Hi, in my previous video on the IBM T221 4K monitor from the year 2000, which has been very popular, highly recommend you watch it. I'll link it in down below and at the end if you haven't seen it, because this will make a bit more sense. I go into quite some detail on the board which we're going to take a look at here, but I got one comment on the video which got me thinking. Thank you very much, Toads Geber. It's not Gerber. It's Geber. Anyway, so how wide do you have to make the traces to carry the same amount of current as a properly executed jumper wire? Whole lot of road, use a fat jumper wire, you don't need roads. So this got me thinking, this could make an interesting video. And if you don't recall, well, you have to watch the video, this is the main processor board out of the IBM 221 monitor. It's got two huge Altera Apex FPGAs, which was state-of-the-art at the time, very expensive, multi-$1,000 FPGAs. And this is the back of the same board, and you can see here that there's these two big jumper wires on here which basically bypass the PCB traces on the board to get lower impedance. So I talked about this a bit in the video, but I thought this will make an interesting deep dive into PCB plane impedances, FPGAs, margins, power supplies, all sorts of stuff, because I think this might be a real interesting example of how something seemingly as simple as a couple of wires on a board actually has really deep technical meaning behind it. And the engineers who designed this board probably spent countless hours actually analyzing and solving this, and why they actually needed to put the wires in place. So I think we're going to go deep down the rabbit hole today. I haven't planned this video at all, but I can think of stuff that is, yeah, buckle up, Dorothy. Kansas is going bye-bye. Right, so we'll do this with two high-res photos of the board here. This is the top side with the FPGAs here, and then we've got the bottom side down here, which is like looking through the board. So you can see the connector here, for example, and that matches up with the connector on the top there. Okay, so everything's kind of like, it's like when you're designing a PCB, you're looking through the board, essentially. All right, let's start out. What's going on here? Here's our power input connector. This comes from our 130 watt power brick here. And you can see that they've got a bunch of vias all in here like this, and that, of course, and the through holes, of course, go through the bottom side. So, okay, nice low impedance connector there directly onto the board. They've got some fuse in here and just some filters there and lots of via stitching in there to go down through to the bottom or inner layers. So all the power comes through this one connector. The power brick's 16 volts at 10 amps. I believe it takes about 130 watts. So we're talking, you know, just over 8 amps for the total power consumption here. Now we have to look at where the power goes, because the entire premise here is, why did the designers choose to put these big, huge thick gauge jumper wires in here? And you can see they actually designed into the PCB, because they've actually got these silk screen, even though when they manufactured this, they just hot snotted it here and ran the cables over here. I'm not sure why, because they've actually, the PCB designer went to the trouble to put silk screen path right on there to show them exactly, and even put little glue markers. Please put some glue there. It's very nice. Okay, the PCB designer was thinking about this when they were doing it. So why have they run these wires? Why couldn't they use the internal traces on here? Now this is, I haven't looked at any layer markers on this board, but assume it's like an 8-layer board or something like that. You might get away with 6 on something like this, but it's more likely an 8-layer board. So usually you're going to have a big, one of those layers will be dedicated to one big ground plane. And this is where we'll get into all sorts of tricky business, and why you might want to run these wires directly over. You'll notice that they're running the negative wire as well, not just the positive. So obviously they're trying to bypass the internal ground plane in here. Why is it so? So why did they do this? Well, there's usually two reasons behind doing something like this. One is that you simply ran out of room on your PCB to put in this case, the high current traces required, big thick traces in there so you can get low impedance, low voltage drop. You simply ran out of routing room on your PCB. But on an 8-layer board like this, you're not going to run out of room. So the next reason is DC impedance. Now, there's two issues on a PCB. One is AC impedance, one is DC impedance. When you see a huge, big, thick jumper wire like this, it means somebody's trying to fix a DC, well, resistance. Basically, you shouldn't say impedance with DC. A DC resistance problem. There's too much voltage drop on that. They're trying to lower the resistance to decrease the voltage drop at a particular current. Remember Ohm's law, voltage is current times resistance. So the more current, well, in this case, let's say we've got our 8 amps flowing across our board like this, then you're going to get X amount of drop over that distance based on the resistance of the traces. It's non-zero. Even a nice big fat ground plane is not zero resistance. But I hear you saying, well, Dave, in practice, a big ground plane, that's going to be good enough for anything. Well, that's not so, as we'll take a look when we go further down the rabbit hole. So now we've got to look at actually where this current is going and where these wires are running and why. Okay, so let's look at our board here. As you can see, it jumps from here over to here. Now, on the top side, that's our big ass FPGA in there. Don't worry about the FPGA on the other side. We'll just look at this one for now. So it's jumping from here and it's going over to here. That's the red wire. Basically, you can see all those little vias in there. So that's jumping over to there. And then your ground is jumping over to this side. So these three caps over here are just some bulk decoupling. That's obviously powering. You can see it snaking through. So the positive wire is coming in here, and that's obviously going into this inductor here, and then we've got a switch mode controller, of course, and then our outputs over to here. So this will be one of the rails of the like the internal core voltage of the FPGA. I'd say, you know, that internal core voltage is probably going to take the majority of current in the FPGA. The I/O is going to take less. So this one here might be the 5 volt regulator, because I believe all this logic is 5 volts. Okay, you can see that positive comes in here. There's an extra fuse here. This goes out to this connector, which buggers off to the bottom board, which is the I/O driver board. That's neither here nor there in terms of the power consumption of this thing. Well, that'll be for the LCD too, because that's where all the LCD is getting its power from as well. So, and that'll be for the I/O board and the LCD as well. But I think most of our issue here is we're going to focus on the FPGA. So how could you have gotten yourself in a situation where you have to run these wires across here? Well, one could be placement of your board. You've got to look at that first. We'll go into voltage drops. You know, I've mentioned the voltage drops are the issue here, but why placement? Well, in this case, they physically needed this connector right here because it's on the back for product, you know, usability reasons. The user has to be able to plug it in. This is all one big like interface on the back panel. So it's got to be here, for example. So you might think, well, you know, you could say that the layout person probably should have, if it was me, I wouldn't have had my big switch-in regs all the way distant from the power connector here. I would have like put them here. Look at all this unused space around here. That's where I would have whacked it. But the problem is, our FPGA's here, and all of this routing comes on the bottom side. Here's our big connector here like this. So all this high speed routing's got to come out to go off to the LCD on the bottom here. And, well, you could argue, well, this could have been up the top and stuff like that. And, well, you know. Anyway, there's layout reasons. Why? So the PCB designer went, well, okay, I'm forced to put my switching regulators up here. That means I've got to get a reasonably low impedance path over here. And if you use the ground plane inside the board, going from here over to here, that's a lot of distance there. We're talking probably 20 centimeters there to get your 8 amps over to here. And you've got your big FPGA under here like this. So any switch-in of your switch-in power supply or your load on the other side of the power supply, even the FPGA itself, is going to cause quite a few issues. So did they goof this from a layout point of view? Maybe, but I'm not going to like, you know, there's lots of reasons that goes into this. This is a month's worth of layout. So yeah, let's just not say that they goofed here, but it's possible. Now, everyone thinks about, when they think about PCB layout, it's all about bypassing. And you can see all the bypass caps in here under the FPGA, right? They've done that well. Look, you've got your large bypass caps. I've done a video on why you need, like, they've got 3 different sizes. One there, like a 1206, 0805, and then 0603s. They've got all different sizes, all the different values for the different frequencies. I've done a whole video on that. It's great. I'll link it in. And, there are 2 different things you have to consider when you're laying out PCBs and designing products like this. One is your AC impedance, and this has to do with all your decoupling and stuff like that. Now, that's one thing, but a lot of designers will forget about DC resistance, and this is why they've come a gutser here and had to add these wires in, because it's not uncommon at the end of a design to you lay out your board, you build it up, your first prototype, you're testing it out, and you go, things aren't quite working, things are playing up and stuff like that. And you might find that, well, your ground paths weren't lower impedance enough. Getting it from one side to the other over here, 20 centimeters was just too far, and you're getting too much DC voltage drop. And that can interfere with your FPGA under here, which is why we need to go to the videotape. We need to go to the data sheet of the FPGA and have a look why this might be a problem, why DC can be even more important than AC decoupling. All right, this is the data sheet for the Apex 20K logic family. This dates from 1998, something like that. So quite an old device, but we've got the EP20K400E here. So I'll spare you the details. Let's go all the way down, all the way with LBJ, and what we're looking for is voltage. And here we go, operating conditions. This is what we have to look at. And this is just, this is not even a deep dive into FPGA data sheets. Have I done a video on that? Anyway, supply voltage. Here we go. So 5 volt tolerant, recommended operating conditions. Our internal voltage, FPGAs will have an internal core voltage as well as an IO voltage like this. And sometimes they've got even more than that. But this is a fairly old school FPGA. The more modern ones, they can have 4, 5 or even more different voltage cores for various things. You have separate ones for PLLs and all sorts of stuff we won't go into. Anyway, look, here we go. Minimum 2.375 volts and 2.625 volts. So you can, so one of those switch mode converters that we looked at on the board, that's going to be a 2.5 volt switching converter to provide the VCC int voltage. And as I said, and the other one will be VCC IO, which is your nominal 3.3 volts, which of course powers all the other 3.3 volt stuff on the board as well. And this is a 5 volt tolerant FPGA, so it will tolerate 5 volts in, even though it's only got a VCC IO of 3.6 volts. Now, look, your 3.6 volt rail here, okay, it's got a fairly wide margin. It's got nominal 3.3, so it's got a 300 millivolt. Minimum is 3 volts here. It's got 300 millivolt margin on the low side. But have a look at VCC int here. That's only 2.375 volts. That's only 125 millivolts less than the nominal 2.5 volt core voltage. So we've only got 125 millivolts to play with. So that's going to include the drop not only on our power rail, but also on our ground rail, because remember, it's a big complex system, so not only do you need a minimum of 2.375 volts at the FPGA chip itself, if you don't apply proper star grounding techniques where you just have the input connector and then you just run the grounds off separately, then the interaction between your different chips can cause logic threshold issues and all sorts of stuff. So if the DC voltage drop on your power and your ground connections go into that FPGA are greater than 125 millivolts, wah, 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 wah. You've come a gutser, and your FPGA, you're now operating outside of the recommended conditions, and all bets are off. So 125 millivolts might sound like a lot to play with, but let's run the numbers on this. And remember, this is an old FPGA. This is not one of the newfangled ones with very low core voltages. If we quickly check out a data sheet of one of those, we'll see we probably don't have much margin to play with. So although it's not directly relevant to this particular almost 20-year-old design, let's look at a modern, say, Altera Stratix FPGA, for example. They've got data sheets just for the AC and DC electrical switching characteristics of these chips. The data sheets are phenomenal. It's not just one data sheet, it's multiple ones. They've got one data sheet just dedicated to getting the power right on FPGAs. This is how important it is. So if we scroll down here, look at all the different types. They've got VCC, which is the core voltage, which is also called VCC int. I guess they've changed it over the years. VCC PT, programmable power technology for the just for the configuration pins. They've got auxiliary ones. They've got battery backup power supply. They've got the IO pre-driver power supply, and they've got the IO power supply. And not done yet, the PLL digital power supply, the PLL analog power supply. So how many are we up to now? 2, 4, 6, 7, 8, 9. 9. And then regular VI, 9. 10 different power rails. 10 different power rails. Modern FPGAs are insane. Like I said before, it's not uncommon to get 4, 5, or more in this particular case with these high-end FPGAs. But let's go down and have a look here at the requirements. VCC. Here's the requirements for just the core voltage of the FPGA. Pain in the ass. Look at this. 0.9 volts. Core voltage. Ridiculous. And then for the programmable stuff, 1.5. Then you need another 2.5. Then you need your 3.3s and 1.8s for all your different power buffers and something like that. And then your programming voltages, your PLLs are another 1.5 and 2.5. Often you can't share them because you need clean power for your PLLs, for example. You don't want to switch that in with your core voltages or your IO voltages and stuff like that. Anyway, the key point I want to make here is 0.9 volts. Look at the tolerance. 30 millivolts. 30 millivolts. That's all you have. 0.87 is the minimum. If you go below that, all bets are off. Your FPGA may not work or may start playing up, doing weird stuff, and you don't want weird stuff in your FPGA. They're already weird enough as it is and incredibly difficult to debug. So at 30 millivolts drop, that's nothing. You remember we had 125 millivolts with the 20-year-old Apex FPGAs. These ones, 30 millivolts, and that includes your positive and your negative rails. You can now see how absolutely vital it is not only to get an accurate power supply, but there's a minimum of drop on your power and your ground traces going to the FPGA. So often you will tweak, it's very common to actually tweak your supply voltage up to, instead of nominal 0.9, you don't want to set it to that. You might want to set it to 0.93, knowing that you're going to get some drop on your traces, and then instead of 30 millivolts, you've now got the difference between that and that. So you've now got 60 millivolts drop to play with when you're laying out your PCB traces. And we'll go to a calculator soon and calculate all this stuff. But as you can see, there's not much to play with there. But thankfully, the Apex one is a bit more tolerant, 125 millivolts. Anyway, but let's go back to our power supply here because we're not done yet. Those 125 millivolt and 30 millivolt margins, as I said, and it's got to get over to your FPGA over to here like this, not only power, but the ground as well. It's got to get through there. It's got to get through all the vias. It's got to get through the local bypassing. And remember, these are DC values. It's got nothing. You can have all the bypassing in the world. It's not going to help you. That's the difference between AC and DC characteristics of a complex device like this FPGA. These are the most complex devices available today, these FPGAs. You think your bleeding edge Intel processors, no, they're like 5 times smaller in die size, 5 times less transistor counts than some of these high-end FPGAs today. These are the most complex beasts on the planet. But it's not only DC, you've also got like low frequency transient characteristics as well. So let's say your voltage is like that, and then it suddenly starts to draw a bit of current. Whoop, it might drop down like that a little bit at higher current and go back up like that. So that is your dynamic characteristics of your converter, because these switch mode converters in here, I don't know which chip they're using, we can probably look it up, but anyway, these are going to have dynamic characteristics as well. The output impedance of these switching converters is something at DC and something slightly different again. Only has to be a smidgen difference, because remember, we're leading edge FPGA, only got 30 millivolts to work with, so that includes not just your PCB traces, but all your switching characteristics of the output MOSFETs and switching elements inside your switching converter. So this is a deep rabbit hole. If you actually want to do this, a designer could spend weeks and weeks or a month just getting this power system right. Bloody scrolling. Anyway, so it looks like on the bottom there's our MOSFETs. You can tell they're MOSFETs because all the pins are tied together like that, and there's just the one gate pin here and here. Okay, so these MOSFET switch in here for our two converters, and then the controller, was that on the top side? These have internal voltage references which set those DC characteristics. So all of the dynamic switching characteristics you could have if you don't have proper layout in your switch mode converter like this, if you don't keep your tight loops, and I've done videos on this, and if you don't keep that tight, you can get extra DC error or switching or dynamic switching errors when your output loads. So if your output switches like this, it might have, two different current levels. You might be drawing, say, 5 amps up here, then it might drop down to 1 amp down here, different modes, and it might do this at sort of lowish frequency, might do it at higher frequency and stuff like that. Then if you don't get if this is, this is very crude, but if you don't get your star grounding points like this one is going off to your load, for example, and this one might be going off to, some other load or whatever, and this one goes to your chip. It goes to your converter, for example. If you have your large switching currents going up like this, and then you connect here your chip off to this point here, then you're going to get that voltage drop all the way along there. That's a very crude diagram, and then you've got an internal reference voltage inside this thing that you've just, you're dynamically switching. When your load switches, your current's going to switch. You might have only 5 or 10 millivolts, but that could change your output reference voltage from your 0.9 volts. It could easily change it down to 0.8, and you're screwed. And that's just with the layout of your little switch mode controller chip. That doesn't include actually going off to your big ass FPGA up here and the voltage drop on those. So that's just ground. I'm just considering ground, not considering power here. So here's the actual chip used on this board. It's the TPS5602. This is the controller, and you can see there's our MOSFETs that we saw before, uses external MOSFETs, and the two big ass inductors that we saw there. And we can go down and we can find lots of various information about this that is pertinent to this particular case. Once again, you're going to have your voltage reference, that's going to be a thing, and it's going to vary over temperature and stuff like that. So you'd have to look into potentially things like that, but really what we're interested in is dynamic characteristics, for example. So let's go down circuit protection, all sorts of hysteresis voltages and things like that. We won't worry about any of that. Typical application circuit, switching frequency. Of course, switching frequency is going to change. It's a complex equation which changes with all sorts of things, and then it can affect various things. And you could come and guts it just there alone. That'd be a whole video. Anyway, under voltage, here we go. Output efficiency, system efficiency, load regulation. There we go. 3.3 volt output load regulation. That's pretty tight. So no worries there over 5 amps. So that's, load regulation is not a problem, but usually something that you've got to consider. That's load regulation is how tight, as you can see, how tight the voltage remains over the entire output current capability of this thing. 1.8 volt output load regulation, that's pretty good. So we're only, 5 millivolts, not even, just a couple of millivolts. So, it's nice and tight. But look, output voltage ripple is, you can come a gutser just on the output voltage ripple. Look at this. I mean, we're talking 50 millivolts. We've only got 125 millivolt margin. That's not including any of our DC drops. So when you include the dynamic characteristics, like, well, the output's not a dynamic characteristic, but it's a fixed and DC rail characteristic, output voltage ripple. And you add that onto your drop. So you add the ripple onto the drop due to your PCB traces. Your PCB, you might calculate your PCB traces just fine, and it could be hunky-dory. It could be within inside that 125 millivolt limit. But you add on your ripple, you forget about that, oops, or your product enters some other different operating mode or something like that, and it draws extra current, and then the ripple gets bigger and bigger, and that can change with temperature and all sorts of, like, what? Like, it's all over the place, right? This is complex. Power up sequencing, we don't care about that. Transient response. Transient response. This is what we want. Look at how much it can change. This is 100 millivolts per division. Remember, we're talking about 120 millivolt margin here. That's not including the DC margin, right? That's including everything. It doesn't care. If you transient outside that for a split second, then as your the FPGA might change modes, your product changes modes or whatever, it drops from 5 amps down to 1 amp or something like that, you're going to have a transient response. Your Kamigates are right there on these dynamic characteristics. Undershooting, overshooting, and that's all that on top of your DC characteristics. There's a lot involved here. But I know what you're saying, Dave. Just switch to just use huge ground and power planes and it's going to solve all your problems. Don't worry about this star grounding and layout and routing and all that sort of stuff. Well, a couple of things. One is that you can often look at all these vias in here. There's vias everywhere. That's chopping up your ground planes. Every time you do it, yeah, you can have blind and buried vias where if your board's like this, then your via only goes between a couple of layers. It's not drilled all the way through like this. And so if you've got your ground and power down here, they can be a nice solid ground plane, but then you've got a more expensive board and it's a trade-off and stuff like that. But even if you had a big gigantic ground plane in here, which is very common for these high-end FPGAs, for that Stratix one we looked at with your 10 power rails, or in a common implementation you might have 7 or 8 rails, something like that. You might dedicate not a whole ground plane to each one. You would have 1 or 2 ground planes, but then you would dedicate like a couple of your layers to power, and you'd be routing your different paths for your power as well. Typically, you'd have them all coming back on the one ground plane. But the problem is, big ground planes aren't magic, because it goes back to, ta-da, bring back you remember this, if you've been watching for a long time, the resistor grid. It's, what was this video, 5 or so, 10 or something? I don't know. Anyway, it was quite old. And you can think of your ground plane as a grid of resistors like this, because that's effectively what it is. Your current, the higher, I've done a video on this, the higher your switch in frequency, the more the current is going to remain. Say you switch in for your source and your loads here, for example, then your current at high frequencies, due to its spreading inductance on your board, will follow the loop, will follow the path directly under the power traces on your board. So there won't be as much current flowing out here and here. But DC, in theory, it kind of will start flowing out. But once again, you've got spreading resistance in here. It's not magic. Think of it as an array of resistors. It is an array of resistances like this. And this is how that you actually analyze. But unfortunately, to analyze something like a ground plane, how much drop do I get on a ground plane? How much voltage drop for a given current? Not easy to calculate. In fact, there's no simple calculators out there to do it. Might be a couple of rules of thumb, but they're not hugely accurate. So you have to use what's called a finite element analysis. You can get real expensive tools to do it, but they very complex mathematical modeling. In this particular case, modeling the drop, like if we had a big ground plane, modeling the drop right across this board over from this power connector over to here like this, and then this over to your, and the output, sorry, to your FPGAs and stuff like that. It's really, it's almost don't bother calculating something like that. So you can do it in theory, but in practice, yeah, no. Okay, so that's why they probably went for the wires, because it's actually a more predictable resistance. We can actually get in here like this. So just putting in a thick gauge wire, you can calculate the resistance of that. It's really easy. And if you're running PCB traces, for example, if you're running power, the positive one on the internal layers, if you had a big, you know, I would make the trace like hugely wide like this, you know, a big thick trace going over there like that, you know, like 20 millimeters wide or something going right over, or even, it depends on how much room you got. Maximize your amount of room. But anyway, you can start, once you get traces like that, you can then start to calculate the DC resistance and the resultant voltage drops. And another thing, to overcome the voltage drops at high currents coming from the output of our switcher converter over to our FPGA over here, some switcher converters you can get a remote reference voltage. So it might take a reference trace, like it's a 4-terminal measurement, so to speak. It'll take ground and power references from under here. So you might have a big power square under here, for example, is quite common. You'll lay out like a big power square like that, for example, and all your, so that's how you get high frequency bypassing, but it's also just one big brick. But of course, all the vias that you've got to drop through from your pain in the ass BGA package on here, drop through, they all split up that plane. So anyway, it gets complicated. Have I done a video on that? But anyway, you'll have a big thing like this, and then you'll have, forgive me, it's vanishing, then you'll have one little trace, a sense trace coming off, which goes back to your power supply. You have, you know, sense traces, and then it actually adjusts for the voltage actually on this square, and it eliminates any of your voltage drop going across here like this. It compensates for it. But as I said, there's dynamic switching characteristics as well to take into play. So it's not necessarily that simple. And if you only got 30 millivolts to play with, woof. Okay, so let's do some calculations. Now, I've actually recommended this tool before, and I recommend it again. It's the best thing out there, and it's free. It's the Saturn PCB design tool. Search for it. It's absolutely fantastic. It does everything. Differential pairs, via resistances. It even does Ohm's law. Does heatsink thermal stuff. It's got pad stack calculators, crosstalk conductor, via impedance, and parts per million calculators, embedded resistors on your board, substrate resistors, and it's just, it's insane. It's the best tool ever. All right, so we'll go to conductor properties here, and as I said, there is a DC and AC element to this. We're not interested in our AC characteristics. We're just looking at our DC voltage drop here. So let's not complicate things. So let's just set it to DC mode here. Well, let's have a look here. We'll have to go over to Imperial. None of this micrometers rubbish. Oh, I'll be swapping back and forth. It's just a habit. Anyway, let's look at our base copper weight, which we've got in our PCB. Now, everyone's used to 1 ounce copper. Now, you don't automatically get 1 ounce copper on a big 8-layer board like this. You might get 1 ounce copper on the outside layers, but more often than not, you'll get 0.5 ounce copper, or you might even get 1/4 ounce copper. But 1/2 ounce copper is the most common on the inside. And then you've got the plating thickness here. This is whether or not your board is plated. In most cases, your traces are not going to be plated. Or your internal layers, they're just bare copper. It's just, they just etch it as bare copper, then they sandwich the extra layers on top and on top and on top, and even your top and bottom layers usually aren't plated. It's what's called solder mask over bare copper, or SMOBC. So if you scrape away, that's why if you scrape away the solder mask on a trace, you'll just get the raw copper. So there is no plating, but if you had it tin plated or something like that, you can add that, and you might see that the resistance down here might halve. Yep. About halve if you plate it, something like that, because your plating might be another 1/2 ounce plating, for example. So anyway, so there you go. So we'll set a bare PCB like this, assume we've got like an internal layer, 1/2 ounce copper. I'm going to go over, and external or internal layers makes a difference. Well, it doesn't make a difference to the conductor resistance here. The conductor resistance is going to be the same, but it'll make a difference to power dissipation. And whether or not a plane is present here, you'll see that it only affects the power dissipation figures, which we're not really, you know, that's not a concern. All we're concerned about is the DC resistance and the current and the voltage drop at a particular current. Because in this case, the plane, you'll see how when you enable that, it puts on a distance to plane like that, 10 mils, 10 thou between the planes, because then you'll get conduction or, you know, radiation from the power trace through to the power plane, and then that power plane can kind of act as a porous heatsink, and that's why your power dissipation will be more if, and further away, if you drop, you'll notice our power dissipation will, can we resolve that? There you go, it goes down. So, you know, 100 mils like that. Anyway, that's got nothing to do with what we're doing today. That's just a side thing. But there's lots of complex stuff that goes into PCB layout. People are, PCB layout designer, they just lay out some traces and, you know, Bob's your uncle. No, there's a ton of stuff. If you've got bleeding edge parts pulling lots of power like we do on this one, and all these different voltage rails with all these different DC, AC, dynamic and static power conditions to meet very tight tolerances, you know, it's nuts. There's a ton of stuff involved. I could do a video on every single one of these properties in every single one of these tabs. Anyway, calm down, Dave. Let's go over to here. Let's say you've got a 20 millimeter trace, you know, a big, thick trace on your board, right? And the conductor length, in this case, what did I say? It was 20 centimeters. So let's go 200 millimeters like this. And the PCB thickness doesn't matter. It makes no difference whatsoever. And our, let's call it 10 milliohms there. Can we solve? Yeah, no, we solved it. That 10 milliohms there. And the current down here actually has to do with the temperature rise. And I've done this in a separate video. So if you've got that 20 millimeter wide trace over 200 millimeters, at nominally 10 milliohms resistance there, that trace will rise by 10 degrees Celsius. It'll actually go up, it'll heat up when you pass 7.2 amps through it. And you can see that we were like talking about 8 amps here, for example. And at 10 degrees is a bit of rule of thumb for temperature rise. You really don't want any more than that. A lot of people set it to 5. I'll often set it like halve it to 5. I don't want a 10 degrees rise and stuff like that. Anyway, 10 milliohms drop on that trace. The 8 amps we're talking about, 80 millivolts drop. That's only one of them. That's just the power trace. What about the ground trace? Bingo, you've got 160 millivolts already. We're already over our RTX datasheet limit. Where was it? Hey, you remember it was only 125 millivolts. So if we take our power trace like this over to here, and it was 20 millimeters wide, for example, nice big, huge beefing power trace, we're going to get a voltage drop across there of 80 millivolts at 8 amps. There you go. And then you've got the extra drop for the same drop again for the ground or whatever. But in this case, that's going to the switching converter. I probably should have drawn that the other way. Let's just say that we had our nice big square in here like this, and then we had our 20 millimeter trace coming over. If it was like, let's just say that's 100 millimeters there, then we'll get half the voltage drop on that. So we'll get a 40 millivolt drop coming from the output of here over to our, let's assume that once it's gotten under the FPGA like that, and you've got your one big solid thing, that there's no more kind of little drops in here, for example. There might be, 2 millivolts or something like that going from one side to the other, whatever. It depends how many vias are in there, like actually breaking up that nice big solid block you've got in there. But you could easily have 40 millivolts drop going from there to there at 8 amps. Easy. And that's just the power, let alone the ground connection as well. But you can argue that if you've got a nice big solid ground plane like this, for example, then you can kind of round it down to 0. You might add on 5 millivolts or something like that. But but there you go, right? You remember we only had 120 millivolt margin. And remember, that doesn't include any dynamic characteristics. That doesn't include any layout issues and how much, drop. If the LCD, you remember we've got our LCD over here as well. It's going to be drawing, it's going to be drawing its own current, so you're going to get extra drop across there. And if you did have one big ground plane Yeah, sorry, you can't see my drawing cursor. Oops. Anyway, if you've got one nice big ground plane like this, getting extra power that has nothing to do with the FPGA across from one side to the other, that's got to share that space. You can get the voltage drop inside this power plane going from here over to here, and you know that could be an extra, I don't know, 50 millivolts or something like that. Who knows? It depends on the load that you're getting, and that could interfere with your voltage drops inside your FPGA like this. You can come a gutser. Let's get rid of all that. That's why you would have a star ground, for example. You would separate, if I was, say, let's say this was all the power, well, it is. This is all the power going off to our LCD panel over here. I would literally split my ground like that, and I would have ground going over separately, and then I'd literally have a split in there like that. I'd have two separate grounds. They eventually join back here, so we've actually split, or it's, you know, effectively like a star ground. This is our point, and then of course then we might have, say, another ground plane going over here to the rest of this FPGA, and maybe if we had some circuitry up here that then needed its own ground plane, we didn't want to interfere with the others, then we would actually split the ground plane like this, for example, under all the memory in the FPGA. That would have one ground plane, then this would have another one, and it'd all come back to the star grounding point like this. So this space in here you would leave blank. That doesn't have any ground plane in it. So you've isolated your, you've isolated your ground planes like this, so that the current flowing from here around here, ground and power to the LCD connector over there, doesn't interfere with your FPGA, or the switching in your FPGA doesn't interfere with the power going over there, and vice versa, DC and AC characteristics as well. But remember, when you split power planes like this, you have to be incredibly careful, because it can be really bad news for EMC. So in this particular case, look, we've got the connector goes down here. This is the high-speed connector that goes off, that's driving the LCD. So in this particular case, the Altera, the signals coming out of here, they're going through these buffers, and then they're going across here. And if you've split your ground plane across here, and that ground plane is used for those switching signals as the return path for those switching signals, you are screwed. It is one of the cardinal sins of PCB layout to split your ground planes and then have the signals running across them like that, because then the currents have to flow all the way, and then your loop is much bigger, and larger loop creates greater EMC. I've done a whole video on that, and yeah, don't do that. So in this particular, for this particular layout here, when I suggest doing the split ground plane like this, I don't mean split up the signal ground plane, which takes that one up. I'd probably have separate ground planes, one that just handled the current for the LCD connector over here, and one that, and then a separate one that handled all the FPGAs and stuff like that. So yeah, I just would have devoted one section on another layer for that. But in this particular case, the FPGA ground would have extended down here like this on a different layer. And you can have like grounds overlapping other grounds, that's fine. So then we can have the separate on another layer, then the ground for the power and LCD connector coming over. So ultimately, I think the reason for the wires is pretty obvious, given the proximity and also this power connector going off to the driver and LCD board. It's because the driver and LCD takes their own fairly large amount of power, and they didn't want that flowing right across the board like this, which could screw up everything. They didn't want it flowing across the ground planes, and they probably didn't have enough internal layers to add some extra ground planes or whatever to do that. Sometimes you can fix this if you rip up your whole board and redo it. Like, you might realize this at the last minute, and like, oh, you know, you're 2 weeks into your layout, and you might realize, oh damn, I forgot about, I forgot about the extra power coming over here. Because often the designers of the schematic And like they may, if they're good, they'll put notes on the schematic explaining how they want stuff done. But it's ultimately up to like which things are important, saying, you know, look, like they'll show it as a star ground and things like that. So the PCB layout person has to know that and stuff like that. But you can, you know, your brain's not engaged. You can spend weeks doing your layout and then you come and go and say, oh, I couldn't be bothered redoing the whole thing. You got a tight deadline or whatever. Okay, well, let's just add some wires on there. It's not a high volume product. She'll be right. But of course, those wires aren't magic. They're going to have voltage drop too. In this case, I think it's about maybe 15 AWG wire, you know, almost 1.5 millimeters, something like that. Ohms per kilometer. It doesn't allow you to, we'll have to convert that. Let me get the confuser. Oh, could have done that in my head. Divide that by 1,000. That's 10 milliohms per meter. So we're looking at 2 milliohms for 20 centimeters, multiply that by 8 amps. We're looking at 16 millivolts drop on one of those wires. That's not two of them, so you might have to double that. That could be take you up to 32 millivolts drop just for getting your 8 amps through there like that. So, yeah. So yeah, whether or not they're doing that voltage drop reasons, I think it's just like a star routing thing. I think they're just trying to avoid all the stuff in here by just manually routing around there, because they probably couldn't have, I don't know why they couldn't have put their planes in here like I showed before, but anyway, I wasn't there when this was laid out. I don't know, and I'd have to get the CAD files. You'd have to look at the actual layout on here. So after, what, 30, 40 minutes, we finally can answer the OP's question. What width trace do you need to be equivalent to the wire? Well, let's say it's 15 AWG wire, which is looks roughly what we've got here. 10 ohms per kilometer. We're talking 1 milliohm for 100 millimeters. So that's not much. But it looks like we can do that with, say, 25... Oh, solve. Let's say just over 20 millimeters. So I was roughly right. Something like that. There you go. 22 millimeters. And to answer the OP's question. And the thing is, like, this is a fairly simple board. Like, as far as FPGAs go, this is, you know, we've got quite a large margin there, 125 millivolts on our rail, which, as I said, you can extend it if you tweak that, tweak the voltage of the converters up here. You put them on the high side, so that's why often way back in the day a 5-volt rail wouldn't be 5 volts. They'd actually set it to 5.25 volts so that all the circuitry near the connector, it'd get 5.25 volts, which would be on the upper side of your 5 volts tolerance on your 5-volt rail. Everything's fine, but by the time it got all the way to the other side of the board with your hundreds and hundreds and hundreds of chips on there, as the old boards were, it might drop down to 4.75, and you're still right. You're still within the margins. But modern devices with their 0.9 volts, 0.8, even lower core voltages, and if you put, you know, you might have half a dozen of these large FPGAs on a big complex board, you can be talking tens of amps, 50 amps, even 100 amps. You can go into triple figures on the amps for, you know, a really complex board like this, and it's a big deal. And that's when you might go in here and go, bugger it, I need 2-ounce copper in. If you're desperate, I need 2-ounce copper in at least a couple of your internal layers. You wouldn't use 2-ounce copper, for example, if you had a mix of high power stuff on your board with lots of other signal stuff. You wouldn't have 2-ounce copper on every one of your 8 layers. You'd tell the PCB manufacturer in your stack up chart, you would tell them that, hey, I need these, you know, layers 3 and 4. They're my power rails. I want those 2-ounce copper, please, plus 2-ounce copper on your ground as well. And you might have multiple ground layers, but then your shield ground layers, for example, I don't care. I could use 0.25 ounce copper. It's not carrying any of the current. For example, it's just like using for switching. It's, you know, it just might have lower dynamic requirements, switching, AC, dynamic current requirements, rather than the big, bulky DC type stuff. But because the problem with 2-ounce copper, as I mentioned in the previous video on this IBM monitor, if you've got 2-ounce copper on all your layers, that actually retains a lot of heat. when it goes through the reflow oven, and then the balls on your BGA may not it gets much trickier. You've got to hold your tongue at the right angle. You might have to call in the greybeard to operate your reflow machine to get that vapor phase set in just right, so that the balls so that you get reflow on your balls, and it doesn't. These balls can come out piping hot like a fresh pizza from an oven, and those 2-ounce copper really retains a lot of heat. If you've got multiple layers in there, wow, it can stay hot forever, and that slows your cool down time, because a lot of your there's a lot of art and science to actually setting the temperature profile. It's not just ramping up the temperature. People think, oh, it's just all about ramping it up like this and then the solder melts. It's also about cooling it down. You can't cool it down too slowly either, because then the solder can enter the plastic region and cause all sorts of dry joints and all sorts of, then you get into material science, and it never ends. But on a real complex board like this with 1,000 pin or 1,500 pin BGAs drawing with 2-ounce copper, it's going to ruin your day. I've had boards which have used really thick 2-ounce copper, and then all of our components like tombstone, all of our resistors tombstone, because we didn't glue them down, and just the slight imbalance between the pads was enough to flip them all up, and yeah, it's not fun. So have I waffled on enough? Have I explained why they put those wires in there? We can't be exactly sure, but hopefully you're still with me down this rabbit hole deep dive. And I could go further than this as well, but I might leave it at that. Hopefully I've given you a taste of what it's like to design these and lay out these high-end boards with these large current FPGA devices. There's so many things involved. People just think about bypassing, but they often forget about that DC characteristic and the voltage drop on the traces, and how when you have big ground planes, you can't really, you can sort of simulate this like on a spreadsheet. You can do it crudely. You can do your own poor man's finite element analysis and try and calculate and stuff like that. But, generally, that's kind of why I like to separate my powers and grounds on the board, not only for very good technical star grounding system reasons, but also then you can start calculating stuff like this, because I've got a block like that, it's going to have X amount of resistance, and then a block goes up like this. As I said, this will actually be the shape of some of these ground planes. In fact, I might pull up a board. I'll show you a real board example. It's not as complex as this, but I think I've got one. Okay, I found an example with a Vertex 5 FPGA. It's a fairly large one. It's 1,136 pins. And as you can see, we've fanned out, a good majority of those. There's, 50 not used or something like that. This is actually a 10-layer PCB. So let's have a look. This is the top layer. Okay, we can actually, and if we turn on all the layers there, doesn't that look funky? You can just see all the various layers. Anyway, let's go back to single layer mode. It's much easier. And so this is our top layer. Here's all our pads. You can see how our vias have been we've fanned out a via from each one. I've done a video on BGA fan out and stuff like that. Don't know if I use this as an example, but you can see the different rails in here. We've got 1 volt, 2.5 volts, there should be 3.3 volts for IO. Oh yes, our 3.3 volt IOs on the outside. That's quite common because the IO pins are on the outside, so your VCC pins are on the your VCC IO pins are on the output. And I believe, we've only got the 3 voltage rails there, so not that many, okay, but this required a 10-layer board to fan this out and get the power in. So let's go have a look at the second layer. Second layer is a GP, so that's ground power. I can't remember what P stands for, but that's just one big ground plane right over the whole thing. So I didn't split the ground plane up. Layer 3, it's just got some high-speed differential gigabit Ethernet traces going out, and just some signal layers going out. There's no power happening on there, but once again, you could have used this layer as an extra one to get power into there because all this spare space in there. And then there's another ground layer because of the high-speed differential pair, 10, I don't know, was it 8 gigabits per second? I can't remember. Anyway, so we had multiple ground layers in there. That's why we needed the 10 layers. And then we've got one layer dedicated to the 3.3 volt rail. So that's just flood fill right over. So this was pretty generous on this board. But if you wanted to get your cost down, we could have. So this one's just signal, and here is where we start to get into our power. So this one in here is, no, that's ground fill. That's just ground fill. Nothing special there. Just decided to put some extra flood fill in there. And here we go. Here's where we do that block. I didn't put a block across the whole thing, but you can see that there's an internal. So there you go. That's our 2.5 volt. So that's coming in from the, it's coming in from the bottom here. So, yep, there we go. It's flowing in. Whoop. There you go. It's flowing in from over here. So 2.5 volts. So it's a reasonably small trace. That wasn't a particularly high current thing, but you can just, that's an example of how that you can just put the big block in there on one layers. But, you know, of course, like, oh, I had to get that trace out there, bugger it. I couldn't do it on some other layer, or I didn't want to, whatever. But yeah, that's an example of having the power block. And we'll see that again. Yep, we see that again. You can see the split down here. So this one is for the 1 volt. This is the core voltage. So this one's going to be higher power. So hence why, look, it's huge. You can see the split all around here like this. Yep, there we go. It's that big pink block like that. Huge, big, low impedance block like that. And that's coming from the, I don't think we had a regulator on here. I think it was coming from elsewhere. Oh, no, it could have. Anyway, so that's coming from up here, and that's hugely low impedance going right down to the FPGA core. So that's a good example there of doing that, that power block and big low impedance running into it. And as you can see, we don't really have many traces coming out on that layer, just a few on the outer pins and stuff like that. But of course, when you're laying out something like this, you would make sure, because of that DC requirement for your FPGA that's fairly critical, you want to ensure that you do route that first so that you don't try and sneak it in later. You know, you really want to take care of that right up front and then figure out how you do your signal traces later. And then the bottom, I don't think we had anything special on the bottom. No, that was just ground. And there we go. We had various, just the bypassing caps and stuff on the bottom. So there you go. That's 1136 pin Vertex 5 FPGA, but not particularly major high current requirements apart from that 1 volt rail did take a bit, but not much on the 2.5 or the 3.3. But every FPGA is different. And I was actually going to get a power estimator for you, because all the FPGA companies have these power estimator programs, spreadsheets, whatever they are, or tools, to you put in your number of gates, your specific family you're using, your switching speeds, what peripherals you're using, what I/O, and all that sort of stuff you're doing, and it will simulate fairly accurately. Depends, you know, garbage in, garbage out, of course. But if you put enough stuff in there, or if you finish your design and then just run the calculator on it, put in all the various factors, it'll give you a very accurate estimation. The power consumption, I wanted to do that for the Apex FPGA, but I went to the Altera tool, power estimator tool website, and it has everything but the Apex series. So I don't know what happened to it. No, it's probably out there somewhere. Anyway. And here's actually a better example of a larger board. Once again, a big 600 and something pin BGA over here. But let's have a look at the different layers. This won't tell you much, but if we go, that's the ground. Oh, sorry, you couldn't see that. My face is a bit. If you go to the power rail, you can see how they're actually split on the bottom here. That just, you know, shows how you can snake things around and just avoid various things. It's not the best example, but it shows you just how you might split up your power planes on a board to avoid voltage drops on one high power section, causing issues on a lower power section, stuff like that. So I think we'll call it quits there. Sorry for the length of this video, but as you can see, there's a whole bunch of stuff involved in this, and I'm not going to say we've scratched the surface, but we've probably only scratched the surface of what you can deep dive into on this sort of thing. There's just so many different permutations and combinations of different scenarios that you can get on boards like this, and how hopefully you can appreciate what a PCB designer, what a professional PCB designer and professional design engineers have to go through for some of these, and consider for some of these complex designs that have all these, you know, high-end FPGAs and things like that. And this one from 2000 in this IBM one is not that complex, but they decided we need to add the wires in there for insert perhaps multiple reasons in there, perhaps at the design stage, perhaps as an afterthought, We don't know exactly. But anyway, it's really interesting. I hope you found that useful. And if you did, please don't forget to give it a thumbs up and subscribe and notify as well. Hit that little bell icon wherever the hell it is, and to make sure you get notifications if YouTube will be gracious enough to send notifications to everyone when I release a new video. Anyway, hope you enjoyed it. Discuss down below. Catch you next time.